Welcome back. We're going to continue our studies of parametric equations by introducing the concept of eliminating the parameter, and then we'll find parametric equations for a graph. We're going to go backwards essentially in that one. Our first objective is to introduce eliminating the parameter. Many curves that are represented by sets of parametric equations have graphs that also can be represented by rectangular equations in x and y. The process of finding the rectangular equation is called eliminating the parameter. So essentially we're going to eliminate t, because t is our parameter. Here's how it works. Given a pair of parametric equations, x equals t squared minus 4 and y equals 1/2 t, we're going to rewrite these equations in one equation in terms of x and y as opposed to two equations in terms of t. So we're going to solve for t in one equation. Choose the one that's the easiest. So I'm going to choose y equals 1/2 t, and I'm going to solve this for t. So that's easy enough to do. I multiply both sides by 2. Flipping things around, I get t is equal to 2y. So now I know what t is in terms of y, so I can substitute that into the other equation. So I take my 2y and I substitute it into my x equation for t. So I get x equals 2y squared minus 4, or x equals 4y squared minus 4. So my final rectangular equation is x equals 4y squared minus 4. I've rewritten that without t in terms of x and y. So what does that mean? Now we can recognize that x equals 4y squared minus 4 represents a parabola with a horizontal axis and a vertex at -4, 0. It is a parabola that opens to the right and has a vertex of -4. It's a parabola that looks something like that. When converting equations from parametric to rectangular form, you may need to alter the domain of the rectangular equation so a graph matches the graph of the parametric equations. So you might have to look at your domains and that kind of thing. So let's take a look at a sample. We want to identify the curve represented by the equations x equals 1 over the square root of t plus 1 and y equals t over t plus 1. So looking at some restrictions here, in y, t cannot equal -1, and in x, t has got to be greater than or equal to -1. So we're going to go ahead and solve for t in the equation for x. What we've done here, we're solving for t from x. So in order to do that, I'll kind of show my work here for you. To get rid of the square root in the denominator, we have to square both sides. So they squared both sides, and we got x squared equals 1 over t plus 1. Continuing to solve for t, we multiplied both sides by t plus 1 to get that out of the denominator. So we got t plus 1 times x squared equals 1. We divided both sides by x squared, and we ended up with t plus 1 equals 1 over x squared. Then subtracting 1 from both sides, we end up with t equals 1 over x squared minus 1. So now we know what t is. So what we do is we take that value of t and we substitute it into the other equation. So I take all of 1 over x squared minus 1 and I substitute it into the other equation. So I'm going to move over here to the left-hand side. I know that t equals 1 over x squared minus 1. I'm going to take that value and I'm going to substitute into the numerator for t, and I'm going to substitute it into the denominator of y for t. So we end up with 1 over x squared minus 1 in our numerator, 1 over x squared minus 1 plus 1 in our denominator. So the minus 1 plus 1 is going to cancel. I've got a complex fraction here. I have a common denominator of x squared, so I multiply the top fraction by x squared. I multiply the bottom fraction by x squareds. My x squareds cancel on the top. My x squareds cancel on the bottom. And I'm left with 1 minus x squared. And yes, I should use vocabulary like my x squareds cancel in the numerator and my x squareds cancel in the denominator. But anyway, we end up with y equals 1 minus x squared. So now I have rewritten this in terms of y and x, my two parametric equations. And you may recognize this is also a parabola that is going to open down and has its vertex at 0, 1. Now remember, we had some restrictions on this, though, what our values for t could be. That's going to constrain what our graph might look like. The parametric equation for x is defined when t is greater than -1, and from the graph of parametric equations, x is greater than 0. So the domain of x should be restricted to positive values. So this is our graph of y equals 1 minus x squared, but we can't have any negative values for x. And interestingly enough, we end up with our graph over here based on our parametric equations. Our graph curve moves in this direction. T equals -1, or t equals -3/4, t equals 0, t equals 3. That is our curve. Our second objective, find the parametric equations for a graph. So we've been studying techniques for sketching the graph represented by parametric equations. Now we want to do the reverse. That is, can we find the parametric equations given a graph or some other description? We know that the graphs of parametric equations are unique. We saw in the previous video that we had two different equations over different sets of time. They had the exact same graph. So that brings us to our second sample problem. Actually, this is two sample problems here. We're going to do a sample A, and then we're going to do a sample B. So find a set of parametric equations to represent the graph of y equals 1 minus x squared using first t equals x, and then we'll repeat the process with t equals 1 minus x. Letting t equals x, we can obtain the following parametric equations. First thing we did is we just flipped this. X must equal t if t is equal to x. And then we took our x is equal to t and we substituted it into y for x. We put t in there and we get 1 minus t squared. So now we have our two parametric equations. We've rewritten these in terms of t. And here, if we put this into our graphing calculator, we would get our particular graph. And we are graphing from t is from less than or equal to, or greater than or equal to -2, and less than or equal to, we could use 3 here. Sample B, let t equal 1 minus x. We obtain the following parametric equations. So rewriting t equals 1 minus x for x, right, we add x to both sides. We can go ahead and subtract t from both sides, and we get x equals 1 minus t. So we have rewritten this to get x in terms of t. So now we have to get y in terms of t. So we take our x equals 1 minus t and we substitute it into our equation. Now remember, our original equation here is y equals 1 minus x squared. So we're going to take 1 minus t and substitute it in to y equals 1 minus x squared. So that's how we get y equals 1 minus the quantity 1 minus t squared. I'm going to rewrite that over here on the right hand side because we have to be careful with the squared. We have to do PEMDAS, we've got to square that first. So y equals 1 minus t squared. We get y equals 1 minus, oops, put my squared in the wrong place. There we go. So 1 minus t squared is a perfect square trinomial. So we get 1 minus 2t plus t squared. We distribute our negative 1, y minus 1 plus 2t minus t squared. We get y equals 2t minus t squared. So here's all the algebra in blue, how we arrived at what y is equal to. So now we've written both x and y in terms of t. So we've got our two equations, and we can put them into our graphing calculator if we want and graph them. We could also do a table of values. If we did our table, we have our t and our x and our y. We might do t's of -2, -1, 0, 1, 2, and 3. And when we put -2 into our x equation, we get 3. And we put -2 into our y equation, we get -8. So we're going to have the ordered pair 3, -8. When we put -1 in to x, we are going to get 2. And when we put -1 into y, we will get 3. And then we put 0 into x for t, and we will get 1. And we put it into y, we get 0. And when we put 1 in, we get 0, 1, 0 for x and 1 for y. We put 2 in for t. To x, we get -1. We get 0 for y. And when we put 3 in for t, we get -2 for x, and we get 3 for y. That would be our graph on the x and y. These would be our ordered pairs that we would plot for x and y. We would show our direction. When we put our x in there is our curve for our parametric graph. And you'll get some more practice with this when I see you in class.